Hello everyone, welcome back to Ivanisvili's webinar. Today we are very pleased to have Paata Ivanishvili from, currently he's in North Carolina State University. And Paata will be speaking on sharpening the triangle inequality in capital LP spaces. Please go ahead.
Thank you for the invitation, Sari. It's my pleasure to be here. So today we will speak about how to sharpen triangle inequalities in LP spaces. So let me start from the problem. LP space, I will have with some measure d mu. D mu is arbitrary measure, no restriction. And LP space is defined in the usual way. Here is the pth norm. And the question is the following. Suppose I have some sequence of functions in LP. When under what conditions on these functions, we can conclude that the sum is also in LP. It's a very simple question, looks like. This question was, as far as I know, was originally asked by Carberry in 2006, and he was interested in non-commutative case. Absolutely the same question, but with Schadt and pth norms, and FIs are, let's say, matrices n by n, for example. But he wanted to have some guess, and before you solve the problem, first you want to understand in commutative case, because you can restrict to diagonal or commutative matrices, and you are in LP. So one way perhaps to answer this question is to take the sum and use the triangle inequality. And perhaps the possible answer will be that this is true if this sum converges, if this is finite. But the question is, can one do better if we know some extra information about pairs Fi and Fj? We know somehow, in a certain sense, they have some disjoint support, not directly disjoint, but we know something about the products, integrals of products of these functions. That's what I put here, orthogonality. That's the question to understand in which sense we want them to be orthogonal so that we can make this conclusion. Now let's look some possible cases. Suppose that FIs have completely disjoint support. Then we have just identity that the pth norm to the power p is the sum of the pth norms. So we can say that the sum belongs to LP if and only if when this is finite. So this is necessary and sufficient condition in case of disjoint support. So that's the good starting point. Maybe we should start requiring this condition. Well, together with something else. And I want to say this, the fact that this is finite, it is much weaker requirement on the functions than what we got with triangle inequality. You can very easily construct numbers when this sum is infinity and this sum is finite. Here p is greater than 1, because when p is equal to 1, this is the same thing. Now let's talk about disjoint support. We want to replace disjoint support by something else, by some similar quantity which would measure in a certain sense that the functions have disjoint support. And what Carberry suggested, let's look at the numbers alpha ij. What are these numbers? You take Fi times Fj, you take p over 2, and by triangle inequality, this is all, by Cauchy-Schwarz inequality, this is always less or equal than the product of norms with constant 1. But suppose we have some control, we know how better it is, and we can put some numbers there. Can we say something about this question if we know some information about these numbers? So these numbers will be kind of measuring the orthogonality. Let's consider L2 case. So here I open parentheses, then I use this inequality when p equals 2, here, and then we can estimate this sum by capital A is the matrix alpha ij, and it's a norm from L2 to L2. It's a vector norm of this matrix times the sum of the squares of these numbers, where this is the operator norm, maximal singular value. And A is this matrix alpha ij. So we got very nice satisfactory answer. So let me say, we got that in L2 we can majorize the sum L2 by what we were getting when functions had disjoint support. And here what we have is that this matrix whose entries are ij's are these numbers. And what we do is that we are measuring the norm of this matrix operator norm. And if this operator norm is finite together with this is finite, then we can conclude that the sum is in L2. Okay, it's a good starting point. We want to understand what is the analog of estimate in LP. We know something else in L infinity. In L infinity, there is this Cotillard-Stein lemma in harmonic analysis. Usually it is stated for operators. That's where it's the most interesting. It has many applications in when bounding some singular integral operators in L2. You can decompose the operator as almost orthogonal operators, and then you can use this Cotillard-Stein lemma to prove that it is bounded, the original operator. So what it says in L infinity is that if you take the sum, measure L infinity norm, then this is less or equal. You know, imagine that I have everywhere, instead of 2, I have P 1 over P. If I say P goes to infinity, that's the quantity I will end up with. So it is supremum over K of L infinity norm of Fk. Now in the Cotillard-Stein lemma, this quantity is slightly different. It's not quite what is written here, because here I had Fi, Fj, L2, and they have supremum over all K. So it has all functions. So it's not exactly, it's not very similar. It's not exactly what is written here. It's a different expression. And there is also square root here. And it says that if this is finite and this is finite, then this is finite. Anyway, we have these two estimates in the literature, and what Carberry did, that one naive way to interpolate, it's not interpolation of these two, but one naive way to interpolate this estimate is perhaps to ask the following question: when P is greater than 2. And that's the question. So we have the sum LP, here we have this kind of sum, and here we have we take this what I was calling numbers alpha ij's, measuring orthogonality. We sum up over i's, and then we take supremum over j's, and then we take to the power 1 over p prime. P prime is the dual exponent of p. Does this estimate hold true? It's, you know, if you take p equals 2, you are not getting L2 norm. You are getting a quantity which is actually larger than this. It's a symmetric matrix. If you take p goes to infinity, you are not quite getting what is written here. But when p is infinity, I think you can, for at least for two functions, you can put this quantity instead of this. So, you know, it's one possible extension. I'm not saying that's the sharpest inequality. You can ask for many functions, but that was the question that Carberry asked. Okay, let's just put the largest quantity. Let's put Schur norm. This is called also Schur norm of this matrix. And as far as I know, this is open problem. We don't know how to solve this problem. I want to say, okay, what about if we consider two functions? Can we solve that problem for two functions when p is greater than 2? And when p is greater than 2, what was written in the previous slide is this sum. When I equals j, this ratio is 1. So you have 1 plus, and I is different than j. You have two functions. You have this number. And the theorem joint work with Carlin, Frank, myself, and Lieb says that the answer is yes to this question. And in fact, stronger estimate holds. Now, what is written here? Let's look what is inside these brackets. I claim that this estimate is much stronger than this estimate. So let's look at what is written in these brackets. If I replace this sum a plus b by 2 times the square root of ab, so 2 times this to the power 1/2, this to the power 1/2, then there is these 2's will cancel, these 2 will cancel with the 2 in the denominator, and this 2 over p will cancel with p over 2 in numerator and in denominator. So you will end up with this quantity if you just use very simple inequality. And by using this inequality, what you are doing, you are making denominator smaller, right? You are enlarging the ratio. So this is better. And this inequality, I just showed that it improves on what was suggested by Carberry. And it is true for p between 0 and 1 and 2 and infinity. And reverse inequality holds when p is in the complement of these intervals. When p is negative, perhaps I want to assume that f and g are non-negative functions. I want to also add the remark that when Carberry proposed this estimate, he could prove only for indicator functions of sets, not for all functions. He verified it for indicator functions of sets. So that's the theorem. And I want to say another remark is that you can think about this theorem as a sharpening the convexity inequality. If you take 2 functions and divide the sum by 2 and rise to the power p, it's less or equal 1/2 than the sum. Now, if you take this 2 and move to the right, you get 2 to the p divided by 2. So you will get 2 to the p minus 1. Now, what is written here, it's 1 plus something to the p minus 1. The claim is that this something is strictly less than 1. Because this is less than this, and this is less than 1 by Schwarz, right? Because you have fg to the p over 2 norm, you can replace it by the product of fp and gp. Okay. Now, let's rewrite that estimate in this form. There is this 1 plus gamma to the 2 over p, where gamma is this another quantity. It's kind of replacement of alpha ij's. You know, once we have this estimate, maybe that's the right alpha ij's one should look at instead of what Carberry was suggesting. At least we know that this is smaller. If you raise it to the power p over 2, it's smaller than that alpha ij's. I just explained you why. Now, I want to say about one more refinement of this estimate. It's another work with Connor Mooney. What we got is the following. So we have this gamma in the previous theorem. Now we can put this expression. 1 plus square root of 1 minus gamma squared divided by 2, 1 over p, plus 1 minus square root of 1 minus gamma squared divided by 2 to the power 1 over p. So here is plus, here is minus. It's 1 over p and everything is to the power p. Again, this is true, p is between 0, 1 and 2 infinity, and reverse inequality when p is in the complement. And equality holds if and only if when fg to the power, let's say positive functions, fg to the power p over 2 equals some constant times f to the p plus g to the p, where this constant belongs to this interval. You know, I want to say that so what I want to say, I want to say that we have this gamma in both cases, right? If F and G have disjoint support, then this is 0. Gamma is 0. So you are just getting this inequality. Here you are getting 1. Here you are also getting 1. If gamma is 0, you have this is 1 and this is 0. So you get inequality, which we know is identity, equality. So it takes into account the case when the functions have disjoint support, it gives you equality. And the right inequality. And what I want to say is that this right-hand side, even though it looks a little bit complicated, it improves with this right-hand side. This is pointwise less or equal than this for any gamma between 0 and 1. Gamma is the quantity between 0 and 1. And you know, one question one can ask, okay, you got some estimate, but why tomorrow somebody else cannot show up and present further refinement of this estimate? I want to say that this estimate is the best possible in the following sense. If you want to estimate F plus G LP norm in terms of 3 parameters, F LP norm, G LP norm, and this parameter, FG P over 2 norm, F times G P over 2 norm, in terms of these 3 parameters, then the claim is that this right-hand side is the best possible in terms of these 3 parameters. You cannot find another expression which will involve LP norms F and G and P over 2 norm of the product FG, which would be smaller than what is written here. So this is the best possible. But another point is that what's the point of chasing for the best possible estimates? Maybe that can give you a correct starting point. What should be the analog for n functions? What should be the correct right-hand side for n functions? This corresponds, if you forget about power 2 over p, for 2 by 2 matrices, it is that sure norm that I was writing for the matrix that Garber suggested. This, I don't know what is this. You know, you have 2 by 2 matrix, right? 1, gamma, gamma, gamma p2 over p, gamma to the power 2 over p, and 1. What is this? I don't know. Is it LP norm? I don't know what is this. Okay, and I want to say one more inequality, because you know, I have this inequality when p is between, okay, forget about negative powers, when p is greater than 2 and less than, and between 0 and 1. But what about when p is between 1 and 2? Garber was interested in that case as well. We wrote reverse, but what if I don't want reverse? I want the same inequality when p is between 2 and 1. And we have the following inequality. Let's take this C, which is minimum between FP, GP, and FG P over 2 divided by FG P over 2 with these powers. The way you should think about it is when FG is 0, then this is 1 in the sense of the limit. The theorem says that for any non-negative f and g, we have when p is between 1 and 2, we have the inequality in the right direction as follows: fp to the p, gp to the p, and there is this c to the negative 1 over p plus c 1 over p to the p minus c to the negative 1 minus c and times fg to the p over 2 to the power p over 2. By the way, if you have any questions, please feel free to unmute yourself and ask, disrupt the talk. I would be very happy with that to answer your question.
There's a question in chat about when p is between 0 and 1, do you use the same powers? But I think you said so, yeah.
In the previous inequality, p is between 0 and 1. Yes, you have the same powers here. It's, you know, when this interval, it is this inequality. When this complement, it's so when this inequality is with this interval and the complement interval corresponds to reverse inequality. And this one extension of in the correct direction, but when p is between 1 and 2, this changes the right-hand side. And the reverse inequality when p is between 0, 1, and 2 and infinity. Now they complement, these two estimates, they complement, and there is also one case left when p is negative, infinity, 0, then we have this estimate. Anyway, I'm not saying that one should pay attention to negative powers, but perhaps the most interesting case is when p is between 1 and 2 in this example, and in the previous theorem when p is between 2 and infinity. And simple corollary of this using induction, one can extend this, one can get the following inequality for n functions. If you have the sum fj, p norm to the power p, it's less or equal than the sum, this sum p to the p, the correct sum when functions have disjoint support, plus some constant times the sum which kind of take care of the pairwise products. I don't know if there is this estimate for Châtain norm for matrices. Let's say, can one get for non-negative matrices at least? I even for two for n equals 2. This I'm struggling to show this simple inequality. Okay, now let me talk about the proofs. I presented so many estimates.
I have a question before you
yes.
go to the question. It seems like it is kind of an improvement of, I'm talking about p larger than 2, improvement of the uniform convexity of AP, which of course you cannot, so which of course is not true, because I think you cannot really improve what is known, but I think that maybe it's an improvement on part of the unit ball or something like that. Is that a good interpretation of it?
You can, well, you want this parameter. If you know some information about this parameter, then you can slightly improve. I think that's the right observation. But if you know nothing about this parameter, f times g to the fg of p over 2 norm, but uniform convexity definition doesn't say anything about the norm of the product.
Of course.
But if we include this extra parameter, then yes, I think we can slightly improve that number.
Mm-hmm. Okay.
Okay, now proof is very interesting, I think. So we have this estimate and we want to prove it. How do we prove it? Let's consider this function of 3 variables, x, y, z, which is parenthesis, open parenthesis, 1 plus 2z divided by x plus y, this to the power 2 over p, everything to the power p minus 1, times x plus y. Let's consider the case when p is greater or equal to 2. Let's just restrict to that case. Now, what do we want from this function? This function is, I claim that this function is concave in the convex cone in R3 in the for non-negative x, y, and z in the first orthant, such that x, y, and z satisfy this inequality. 0 is less or equal to z, less or equal square root of x, y. This function is concave function in this convex cone. It's a convex cone. Let's verify this claim. First, notice that this function is non-homogeneous. If I multiply variables by lambda, positive number, then I can pull out lambda, right? Because lambda z, lambda x, lambda y, lambda cancels here, and lambda just will appear from this sum. Now, what it means is that if you have a one homogeneous function in 3-dimensional space in some domain, convex set, and convex cone, and you want to check that it is concave, it suffices to check that it is concave in one section. in a section which intersects the subgraph of this function along, it should be intersecting all rays of the subgraph is the cone, right? It should intersect along all rays. It should intersect all rays of the cone. It's a simple fact, right? If you have a cone and you want to check it's convex, you just check that if you take intersection with a hyperplane, the intersection is convex. Now, in this intersection x plus y equals 2, your function just becomes 1 plus z to the power 2 over p, and p minus 1, and then this is constant 2. So we will get that, we want to check that this is concave when t is between 0 and 1. 0 and 1, why? Because when x plus y equals 2, then square root of x plus y is less or equal to 1. And z ranges between 0 and 1. For example, it's not, one more remark is that this function is not concave when t is greater than 1. Indeed, you calculate the second derivative, it's written here. So here is p minus 1, p minus 2, and you see that it is indeed less or equal to 0 when p is greater than 2, because this is positive, this is positive, this is positive, and the only thing that is negative is this one. T is less than 1. You see, when t is greater than 1, it becomes convex, but we want concavity. Okay, I just showed you that this function is concave. Now, why do I need this? I want to use the one more claim, which is this following pointwise inequality. That if I take b, I plug numbers a to the power p, b to the power p, and ab to the power p over 2, it is greater or equal a plus b to the power p for all non-negative real numbers. The way you should think about this inequality is that these triples, what is written here, they parameterize the boundary of the convex cone that I had here. This convex cone, the boundary is when z equals square root of xy, right? And this corresponds that this number equals square root of this times this. So we are looking restriction of b on the boundary of the convex cone. And the claim is that b on the boundary majorizes this obstacle condition. Let's think about it as an obstacle condition. Now, do I want to prove this inequality? Let's skip it because it's a technical step, and let's skip this inequality. Actually, this is the most, perhaps the most delicate case in this argument, where hard analysis lies. Okay, now I have this function. Now we know that it has this pointwise inequality, which I rewrote in this way. I know that b is one homogeneous. I can, this is true now for any non-negative functions, f and g. Because by one homogeneity, I can pull this out, 1 over f plus g to the p, and move it to the left-hand side. And it's exactly what I had in the previous slide, this pointwise inequality. Now, one moment. So we have this for any point, there is variable x, right? F of x, g of x, for any point x, this is true. And for any non-negative functions, now what we do is that we integrate with respect to probability measure. F plus g to the power p d mu divided by the integral f plus g to the power p d mu. And we apply Jensen's inequality because b is concave, and when we integrate, these points are on the boundary of this convex cone. So we want, the only thing we wanted to make sure that this function is concave in the convex hull of this surface, which is exactly this convex cone. So you can apply Jensen. Well, what do we get? 1 is less or equal if we put integral inside by concavity. And now if you do some computations, and what is d nu? D nu is this, right? If you cancel f plus g to the p with f plus g to the p, what do we get? We get integral f to the p d mu divided by this integral, and divided by this integral in all three variables. Then you can pull out this integral and rewrite this inequality. And what we got here, it's exactly what Carberry was asking. I'm sorry, what we wrote in theorem with Carlin, Rupert, and Lee. And that's the proof, essentially, when p is greater or equal to 2. Well, one can ask, what was the difficulty, right? Where should we look? What was the hardest point? There are two things. One thing is that from somehow I guess this function, which I have not explained to you, where does this function come from? Well, there was also this pointwise inequality, which I also did not tell you why I believe it would hold. So there were two things: guessing the correct concave function and having this obstacle condition. And these are where one needs to work. And I'm going to explain you how to guess this function and how to make sure that this obstacle condition also holds true. Now, before I explain you, let me tell you how can you use the same argument to prove a refined version that we had with Connor, this inequality. Now, for this inequality, we should consider this function of three variables. It's written here, 1 plus square root of 1 minus 2z over x plus y square divided by 2 1 over p, plus the same thing with minus 1 over p to the power p and multiplied by x plus y. Let's consider this function. I claim that, again, it is concave in our convex cone, omega, which is the set of points where 0 is less or equal to z, is less or equal to square root of xy. And it satisfies this obstacle condition on the boundary of this cone that we want. And then in absolutely the same way, you can proceed and prove the estimate, this estimate. Again, the same question, right? So how to find this function? So what we want these two properties. We want to find function. Let me explain you how can you find this function. Suppose nobody gave you a priori this function and you just start, but you know what you want to do. You want to find a function in this convex cone, which has this obstacle condition and it to be concave. Well, when you apply Jensen on the right-hand side, you get this function. You want also this function to be smallest pointwise. You want to choose B to be smallest pointwise such function with these two properties, kind of minimal concave function. So one question is how to find such a minimal pointwise concave function, B, of three variables. And another, perhaps the most interesting question is why the result that you will get with this approach will give you the best upper bound in terms of these three parameters that I was talking, f to the p, f, norm of f, norm of g, and the norm of fg in terms of these three parameters. Why this approach gives you the best possible bound. Now, let me first answer the second question, why this approach gives you the best possible bound. And then I will talk about how to find minimal concave functions over which have certain obstacle condition in some convex sets. So what we want these two properties, right? Suppose you found this function. Suppose you have some candidate and you know it's minimal concave function with these two properties. And here is the theorem, a simple one, which says that then this B also coincides with the solution of this optimization problem. It's a supremum B of x, y, and z, the function that you find here, minimal. It's a supremum of over test functions, f and g, where you maximize, take supremum of this f plus g, the object that we want to estimate from above. In turn, and you fix LP norm to the power px, LP norm to the power py, and this to the power p over 2z. it coincides with this with the solution of this optimization problem. So that's what it means, that it is the best possible to estimate this in terms of these three parameters. You know, one needs to be a little bit careful. If I remove p here, let's say I just fix the pth norms and p over 2 without this power, then the resulted function will not have any nice properties. It won't be concave. Well, maybe, but it won't have. It's very important that it is fixed exactly in this way. Now, once we have this theorem, then you are more convinced that that's the case, that we need to find minimal concave function in this domain with this obstacle condition. B is one homogeneous. It follows from this definition, from this theorem, because if you scale variables, let's say you write here lambda x, lambda y, lambda z, then what you can do, you can scale the optimizers as well. You can take lambda f, lambda g, and then this here lambda will be pulled out with exactly like in what, so b of lambda x, lambda y, lambda z will be lambda b of x, y, z. And another thing you can notice is that on the boundary of the convex cone of omega, we have actually equality. Bxy square root of xy equals x to the 1 over p plus y to the 1 over p to the power p. What it says is that this obstacle condition that you have on the boundary, it is actually equality. You know, what is written here, it's exactly this, but with equality. If you replace a to the p by x, then this will be x to the 1 over p, right? xy and square root of xy. So it is this one. It's reasonable to expect, you know, if you are minimizing function and you want it to be concave and it has some obstacle on the boundary, well, if the boundary were extreme points of the domain, then it should coincide, right? It's because you can think about the solution as you take the convex hull and then you look at the upper boundary of this result. But in our case, this boundary is not quite extreme points, but because it's a convex cone, but because of one homogeneity, it's still true that it coincides with the boundary. Now, how do you find such function in this convex domain with this boundary condition and minimal concave? One more reduction, we can say one more observation is that we need to find B only in the section. You take this domain and you intersect with some hyperplane. If you find, you know, it's defined in the convex cone, right? I'm saying let's look at the intersection of this convex cone with the hyperplane and let's construct B in that section. There will be induced boundary condition, induced from what is written here. And you can construct a concave function with that induced boundary condition, minimal one. And then if you extend the result by one homogeneity, the claim is that the resulted function will be minimal concave function with these two properties, 1 and 2. Now, what is this intersection? It's upper half disk. If you draw the unit disk on the plane, it's upper half part. Well, if you need to move picture a little bit into the XY plane. So the question is, find convex envelope, upper boundary. So we need to find function in the upper half disk, minimal concave, which has certain boundary condition on the circle, on this upper half circle. And you can draw what is space curve. It is S square root of 1 minus S square, 1 minus S1 over P plus 1 plus S1 over P to the power P, when S goes between -1 and 1. If you look to the space curve, these two coordinates, they parameterize upper half circle. And this third coordinate is the value of the function B induced from this equality on this upper half circle. So you have a space curve, which if you project on the plane, it is just the upper half circle. And you want to find in this upper half disk concave function, which coincides with the space curve, which has this wire. let's think about the space curve as a wire. How do you find such function? One thing you can say immediately that take the convex hull and look at the upper boundary. Yes, but we want to have a formula. Another thing is that we can say, perhaps we can use Karateadoris theorem. We can find its value of the function inside the upper half disk. It's the supremum of the three linear combination of the points of the space curve. And you can try to solve that optimization problem for every point. But it's a very, I think it's a hard task for each points, for each triples, for each point inside the half disk to solve this optimization problem, because we want to find function in the full upper half disk. Here is the theory which was very well, okay, we studied for other problems back in St. Petersburg with my collaborators, with Nikolai Osipov, Stolyrov, Zatitsky, Vasunin. With this group of people, we studied similar questions in a slightly different setting for different extremal problems, but the questions were also reduced to finding minimal concave functions in non-convex domains. That case was non-convex, much difficult. Here we are in the convex case. And what it says, let me just summarize. What it says is that first what you do is you look at the curvature. And the curvature has a positive sign. The next thing that you do is that you look at the torsion of the space curve. Here is the torsion. It's determinant of gamma prime, gamma double prime, and gamma triple prime. And you look at the sign change of the torsion when S runs on this -1 to 1. And you can notice that if you look at the sign change of this torsion, the torsion changes sign exactly only once from minus to plus at point S equals 0. When P is in this interval, exactly 0, 1, and 2, and infinity. And it switches, it changes sign from plus to minus when P is in the complement of this interval. That explains the reason that we are getting different functions. So let me show you a picture. Here is the wire. Let's say this is my wire. And the question is to find the minimal concave function which coincides with this wire and which is concave inside. Okay, if you project this wire, let's think it's a disk. It's a different wire. It's not upper half disk, but let's think that your domain on projection was disk, and which is minimal concave inside that disk. So how do you find this envelope? You can take the convex hull and then look at the upper boundary. On this picture, I tried to imitate, I tried to draw the actual solution. Actually, I constructed it. It's linear along these line segments. It's linear along these line segments. Then there is this triangle, which is domain of linearity, where the function is completely linear. Then there are these line segments. Then you see that it's also linear along that line segments and along that line. And there is one more triangle on that side. Now for this wire, the solution is this. With high probability, of course. Now, how do we figure out where to start constructing this line segment? Where to start kind of increasing these line segments, and where is this angle? Where to put this triangle? Kind of find these critical points, right? One point, this point, and how to find these chords, how to find the parameterization endpoints of these chords. So here is what that kind of theory that we did in St. Petersburg says. You do the following. You look at the torsion of the space curve, and you look where the torsion changes sign. Torsion at this point where you see that constructed, there are constructed chords, torsion is 0 at this point. Here it is negative, here it is positive. So at this point where you start constructing these chords, torsion changes sign from minus to plus. And that's the reason you can construct the chords. Now, at this point, torsion changes again minus to plus. The claim is that everywhere where you see these chords coming, increasing, the torsion at that point changes sign from minus to plus, provided the curvature is positive. If curvature can become 0, then it's not always true. But here it is the case that the curvature is positive. Now, where are the angles sitting? Where is this angle? It's not true that the angle is sitting at the place where the torsion change is signed from plus to minus in the opposite direction. That's not the case. No, that point can be somewhere else. The angle you need to find, and I will tell you later how do you find that angle. But I also want to warn you that there could be points, other points, where torsion change is signed from minus to plus, like here. But it's not always necessarily true that you start always construct the chords from that point. No, that's not the case. For some points, yes, for some points, no. And it's a question of how to find for which point it is true. But local, if you ignore, for example, if you just look at this neighborhood and ignore the rest, then it is true that if you start constructing, it is minimal concave function. You know, the picture is minimal concave function because you cannot take this point on the chord and push it down. You break the concavity. Now, so that's what I said. And how do you find the chords? Suppose this is one endpoint, gamma A, and this is another endpoint of the space curve, gamma B. So what do you know? You know that if you draw a tangent line at this endpoint and tangent line at this endpoint, and you look at the chord, these three lines, they lie in the same plane. If you draw a tangent plane passing through this chord, it will be above the concave function and it will be tangent along this chord. So the equation, how do you find the endpoints of the chord is this. It means that this tangent line, gamma prime A, gamma prime B, and gamma A minus gamma B, the whole vector, lie in the same plane. You solve this equation. And that's how you find the endpoints of the chords, which parameterize this, which parameterize this endpoint. That's how you find the endpoints of the chords. So essentially, place where torsion changes sign from minus to plus, you draw what we call cups according to this equation, and angle you need to find, but it's not always the case that the endpoint of the angle coincides with the sign change of the torsion from plus to minus. And the same thing happens in that point, but in our case, the picture is much trivial. We have very symmetric space curve, which is symmetric along the y-axis in this example. The space curve is symmetric, so it has a very trivial solution. It just turns out to have a very trivial solution. Now, of course, the question to solve the problem for n functions that Carberry asked. Well, you can start adapting this approach. It's also clear which function you need to take. You know, when we had this this inequality, right? It was not really difficult to guess. Well, first you want to have the right inequality. The right inequality was, so I erased it, right? I'm sorry, here it should be not this inequality. We are proving our inequality in the theorem. Where is the theorem? We are proving this one. We are proving this one. I wrote Carberry's. Carberry's is weaker. This is much stronger. We are proving this inequality. And you can kind of guess what is your function. And the Carberry has this matrix norm for this matrix. You can also guess what should be your function B. I'm not saying that it will work, but you can start just taking that function B of many variables, and you need to figure out what's the correct domain and find out whether that function is concave. I have no idea why is this the case. Or you can just honestly fix all parameters. It will have many parameters, n parameters, actually many, because you want to fix the LP norms of Fi's. And you also want to fix LP over 2 norms of Fi times Fj. So it will have, I think, n plus n times n minus 1 over 2. Those many parameters, you want to find what's the domain of the function and what's the obstacle. Obstacle condition is clear. It's just the sum of Fi's to the power p. And you want to find the concave function in that domain with that obstacle, and it seems at this moment not very feasible to solve that problem, because what I showed you about this space curves torsion, this theory works very well for two-dimensional space, for space curves in 3D. In higher dimensions, we had some possible extension, but things become complicated. I think, how much time do I have?
It's right about maybe like another 2 minutes.
Actually, I think I will stop here, and it's
okay. Okay, thank you so much. That was a pretty pretty difficult papers, the argument to follow. Let's see if we have questions or comments. Anyone? So in your function B, you have this z over x plus y, but z is like sort of independent of x and y. Like, how does it account for this orthogonality condition? I mean, like, conceptually, where does that come in? Like in this function, it looks like it's just arbitrary number, right? So there is no.
Yes. So it's right. Let's see.
Yeah, that's right there. Yeah.
Yes, I want to show this. So here is the z. The z which appears in the formula, it is this parameter, and if f and g are 0, we just take z equals 0. In this, I'm sorry, if they have this joint support, z equal, but the only constraint from when you fix these three parameters, x, y, and z, this z, the only constraint you have is that z is less or equal square root of x times y by Cauchy-Schwarz. And that defines the domain. So when you define some optimization problem, it's not true that it is well defined for all x, y, and z's. You want to find out for which, what are the admissible variables, x, y, and z. Admissible is, it's a proposition that this is the admissible domain. For any points x, y, and z which lie in omega, I can always find test functions f and g which have this, which satisfy this equality. So z measures this norm. That's what is z.
All right, thank you. There's a question in the chat by Lee. Do you see the chat?
Let's see, I'm not sure.
It says, what do you conjecture for positive matrices?
What do you conjecture for positive matrices?
Yeah.
Okay, so one thing I don't want to say I conjecture, I think it's a good question to ask. One question is, I would be interested if you could prove for positive matrices, positive semi-definite, this inequality where P is the Châtain norm and P is between 1 and 2. Okay, and even for two functions, when I have f and g, is it true, for example, is it true that f plus g Châtain norm p to the power p is less or equal the sum of the Châtain norms p times this constant and times here you will have one number, right? A b Châtain norm p over 2 times. I think I want to put a b times a b star and well, the Châtain norm of a b. That's what I want to put. This I don't know. I'm struggling with that one. And another thing is, of course, the question of Carberry, which was asked for many functions. Does this hold for non-commutative case? Or what's the right norm of the matrix alpha ij one needs to put? Perhaps maybe this is not the right one, but I don't know. But does this hold for non-commutative case? That's the original question of Carberry. And then he asked, does it hold for functions? We don't know yet how to prove it for functions.
Okay, any other questions or comments?
I have a question. We all know Clarkson's inequality. Maybe not all of us know Haner's inequality. Maybe if you will permit me to share screen, I'll put it on the up for you. Olaf Haner.
Yes.
Everyone is aware of this inequality. It's perhaps not quite so well known. I'm wondering if there could be some interesting interplay with that inequality and the work you've been doing. Should I display the inequality or everyone knows it?
I can actually share my iPad and I can write down the Haner's inequality. So one moment.
Yeah.
My Swedish friends tell me it's not Haner, but Haner.
Haner, okay, I didn't know.
Neither did I until I went to Sweden.
So let me share the iPad. I will write down. So let me, I think I should rotate. So does it, why it doesn't rotate? Okay, so Haner's, I think what it says is that if I take f plus, does everybody see what I'm writing?
Yes.
Yes.
To the power p plus f minus g p to the power p, less or equal or greater equal, it depends on I guess f p plus g p to the p plus and then f p minus g p to the p. Let me check, but let me.
If p is between 1 and 2, you have that inequality with in the reverse direction.
P is between 1 and 2, and I have, so this is correct, right?
If you change the direction of the inequality, if Wikipedia is right, the inequality you have to.
Okay, then let's write like this. Now this is correct, right? Am I right?
I don't see it well again, Wikipedia gives a different inequality when p is I can show you
so I think Wikipedia gives this inequality when reverse inequality. Okay, let me say this way. Wikipedia gives reverse inequality when p is between 1 and 2.
That's right? What I see. Everyone can make mistakes.
Yes, and the reverse inequality, the previous one that I wrote, reverse when p is in the greater or equal to 2. So
there's some constant involved in that case, though.
Say again?
Yeah, when p is greater than 2, there seems to be some constant involved, like 2 to the p. But anyway, so why don't you talk about this one then?
Okay, let's talk about this one. So I know one thing that so I don't know relation, any good relation between what we are doing, because we have this parameter f and g to the power to the norm p over 2. We have this parameter, and this parameter is not involved in Haner's inequality. It has kind of, there are only a few parameters. There is this parameter, and p and g norm of the functions. But since you mentioned Haner inequality, I want to say something else about Haner. Is that there is a question to have Haner for n functions. For n functions, and I guess the way they write is that sum epsilon I fi LP norm to the power p is greater or equal, and then we have we just put, so we have this, so we have expectation, I think. Expectation.
Expectation on the left, not here.
Yes, here is also expectation. Epsilon i's are plus minus 1. Expectation, and then we just put, I think here we leave power p, and then there is the sum epsilon I fi fi to the power p. For p between 1 and 2. Say again, sorry.
On the right hand side, what did you write?
On the right hand side, it is expectation of the sum epsilon I times pth norm of fi.
Okay.
Let me see what I'm writing. Pth norm of fi. There is this question, and there is a paper, old paper I found, which claims they have proved it, and they call LP space of Hanner type P if this inequality holds true. And that paper has a gap, I want to say. I want to use this opportunity to say, because the question is essentially to show that this function, if you use the same approach that I was describing here, is that if you have this function, which is average of the sum of epsilon as Rademacher plus minus 1, ui to the power 1 over p, and everything to the power p. The question is that if you define this function for a u1, un greater or equal to 0, to show that this function is concave, okay, convex when p is between 1 and 2. And what that paper does is that they show that this function is separately in each variable convex. But to prove, in the proof, they use Jensen's inequality, but to use Jensen, you want jointly convex. So since you mentioned Hanner, I want to say that there is this interesting problem, which if you use absolutely the same thing, and it's absolutely the same Jensen's inequality, but applied to this, let's call this function B, to this function B. So the only thing one needs to verify is that this function B is convex for this power P, and it is concave when P is greater or equal to 2. And I have no idea how to do it. This was done by Hanner when n equals 2. That's what he did. But when n is large, you want to check something is convex for arbitrary n. It's kind of dimension independent phenomena. I have no idea how to do it. You can calculate the Hessian. It's some strange matrix. Why it has a definite sign? I don't know. But I can verify it very easily. I'm sure you can also verify it when p equals 4. Okay, something I want to say. I sent email to that authors of that paper, but I did not receive any response. I'm not sure they are alive, because I received that some email doesn't work or something. It's some Japanese, old Japanese journal. Okay, but the only relation I know that you can use the same approach, absolutely, and to prove n Hanner inequality for n functions, the only thing you need to verify is that this function is convex for this power.
Okay, thank you. You can't somehow do something about f times g in terms of f plus g and f minus g? Like, I don't know, crazy thoughts. You are complimented for showing the power of hard analysis, and I want to say that I really enjoyed the mixture of hard analysis and differential geometry. That was fun.
Thank you.
Is the concavity, the question that you ask about the concavity for p larger than 2, what about the other even integers? P equals 6, is it?
I think one can, okay, I checked by hand, it was some computation when P was, I think you can compute, maybe you can compute with P equals 6, it will be more computed, but that's not the right approach.
No, of course not.
if P is not integer, I have no idea. There is a Hessian. It's a very nice matrix. Okay, not very, it involves, it's dimension independent thing. If you want to construct concave function, non-trivial concave function, arbitrary dimensions, there are simple ways just to somehow take the sum of concaves, but this is, I think, one next trivial example. Or maybe if there was some kind of duality theorem, which would say that if you prove concavity in this case, it implies convexity in this case, and that was true when n equals 2, and it is in the paper of Ball, about sharp uniform convexity. They have this duality theorem that if you know that it is what was the theorem? If you know it is concave in this range, then you know it is convex in this range. Hanner in one case implies the opposite Hanner in another case. But I don't know even if that kind of statement holds for arbitrary functions when n is greater or equal to 2 for arbitrary. And this I don't know, because there was computation was just still computing derivatives, but no, not quite. There was something else.
All right.
It's very simple. I don't know if you. Yes. Okay. I'm so sorry.
Okay. Thank you so much, Paata. So we appreciate the talk. I'll stop recording, but we can still continue chatting after that. Okay. Thank you.